been having some luck getting into that. There is a learning catalytics session that you should see open. There's no question yet. It'll be maybe in about 10 minutes. I'll offer the first question. I'm not quite sure whether or not you have to type a session ID or not, but if you do, it's displayed on the screen out there, and I'll put that up again when we do our first question, just in case you need that. I was looking, I've also got the Ed discussion board open over here on classes. Oh. See, there's some stuff already I'm missing. But I noticed that someone asked about the lab groups and things. One of them, she didn't answer here, are we supposed to complete the mechanics modules before labs? No, those are supposed to be done in class. So I've posted, or Roya has posted these activities on there for you to kind of look at ahead of time. But the whole idea with practicals is there's no homework aspect to it. You go there and do the work during practicals with your friends that you'll be assigned to. But this week, it's just the first hour only of practical, and it's not super formal. There's going to be a diagnostic survey kind of thing on which you will write your student ID number, which is some number that starts with 1 and it has, I think, 10 digits in it. And that's worth like 1 practical point. Oh, penguin, you stop, you. This is my friend, a little metronome penguin, but ticking away the seconds. Let's turn him off for now. I think you have been split into groups, which tell you which practical room you go to, which is either MP 122 or MP 123, and they're right beside each other. So if you can't figure out the group section, don't worry. In fact, we're even going to post your name on a little list outside the door, so if you just want to walk over there, you'll find your room. And even if you sit in the wrong room this week, I think it's probably fine too, because again, as long as your student number is right, you'll get the marks for that survey. But it's weird. To find the groups, you go actually outside of the course structure, and you go to groups. It's way over on the left side of your Quarkus menu, and that's where the group shows up. So you can click within Physics 131, and you won't find it. You have to find your group. And I guess the idea is that groups might include things that are extracurricular and are not part of any course at all, and that's why Quarkus puts it over there on the left. What else did I see? I saw something, has anyone successfully bought the physical textbook? So this is super confusing. So when you go to the e-text, you see an option down at the bottom that says, buy the printed textbook. And then you click on that, and it says currently unavailable. So that's not the right link. The right link is sort of, again, over on the left, and it says Canadian print offer. And that's you. And then you click that. At some point, there's a promo code, which is PhysFall22. You can see it there, to get your 50% off. And then it ends up charging you $32.50. And apparently, they will mail you this book. The only worry I have is that it might come loose leaf with 3 holes punched in it, so you might need a binder to put it in, so which would be extra as well. So, but I hope some people are successful in doing that if they wish to do it. And I can look over here and see if there's anything else coming up. Yeah, the pre-class assignments, all those are just those DSMs. So if you're going through those according to their deadlines, then you're all good. There's no individual pre-class lecture. Yeah, what's the difference between the syllabus draft and there's not any difference, I don't think, between the draft of the syllabus and the syllabus I posted. Maybe a couple little details, but the real syllabus has been posted now. It's good to have those because those are the rules for the course that I submitted up to the undergraduate chair, and you can hold me to them. Okay. Yeah, and so another question that was on that I see on the Ed discussion is just to confirm: are the pre-course diagnostic quiz and post-course diagnostic quiz for participation mark only? Yes, it is just for your participation. So In fact, a lot of the questions you'll see this week are just about your attitudes in science and really have no correct answer. They do, I guess, have an answer that I'm kind of looking for, I guess. And another way of putting that is that when people are asked about their attitudes in science, who are like scientists or graduate students or something, they tend to answer one way as opposed to another way. Anyway, it doesn't matter what you answer. I would just like you to answer honestly. And you get the 1 point for having done it and written your student number properly on the top. I think there's a question somewhere in there to make sure you're still reading. And so I think that might be the one that you need to answer correctly in order to get that point. You might see that as you're going. And this is sort of getting into content now. So I refresh, see if there's anything else coming up. Just out of curiosity, maybe some of you, and I know a lot of you, took physics in high school. Maybe like in grade 11, grade 12, last couple years of high school. Can you raise your hand if you did not take physics in like last couple years of high school? I see quite a lot of you. Thank you for sharing that. You are not alone if you look around. It's not a prerequisite to have high school physics in this course. And I think there's around 200 students that didn't. And so my goal here is I'm going to start from the beginning. We're going to start with kinematics. And to put it another way, so my daughters, both of them went to Etobicoke School of the Arts, which is a great school. They had, one was in flute, the other one was in visual arts. But it's an art school, and they took physics. There's a physics course there, and I met I will not name who the physics teacher was there, but really his philosophy was sort of physics is all about ratios, and there's two. There's V equals D over T, and F equals MA. And then there's all the permutations, which is, oh, well, D could be V times T, or T could be D divided by V, and then F not only could be MA, also A could be F over M. So the entire course of grade 12 physics was kind of working with these permutations of these letters, and there was worksheets and numbers, and you just find the two numbers you know, and find the third number you didn't know. And so I think a lot of students had come from that particular physics course, come to here, realize they don't even know what the F stands for, and it actually hurt their ability to do physics here and kind of understand the concepts and do well on the tests here. And it was a very different experience. So if you didn't take any high school physics, it might even be better than having taken a bad physics experience in high school. So does that make sense? So what is F? So F, so you don't just find a force by timesing M times an A. That equation, Newton's second law, is about the net force, okay? And so that's about the vector sum of all forces that are acting upon an object. And so I'm going to kind of go through that, and I want to start with concepts first, and then get to the equations. You need to understand what all those letters mean. You need to know what acceleration is, first of all. And I find, actually in this course, getting started, so over the next maybe 3 weeks or something, getting familiar with those laws is what and what the concepts are behind them is what we're aiming for. That's my goal. So it might be a review for a lot of you who didn't raise your hand, who have all that experience, but bear with us, and I think hopefully you'll see it from a sort of a different perspective. But So chapter 1 is kind of more about just sort of intro stuff about modeling and things and what is physics. We went through it a little bit on Friday, but physicists, collect, analyze experimental data. They make explanations for what they think is going on, and then try to test them out. We sort of walked through that whole scientific method sort of idea. Creating different representations, so using pictures, like draw a diagram is a really good step when you're solving a physics problem. Making graphs. There's bar charts, which come up a lot in this textbook, especially when we get into conserving energy and conserving momentum, is to try to add up some bar charts. So if you've got a positive, sometimes it cancels out the negative on one side, sort of the energy before you do something in the system and the energy after, they have to sometimes be equal. And so that's what a conservation is when something, the total energy does not change over time. It just gets converted into different types, and so different bars on a bar chart. And then the equations kind of come in. Mathematical relations is usually these equations like F equals ma. We do get there. And then trying to test those and trying to see if what we see really matches up with what the equations are telling us. And to start off, we do this simplification. And of course, there's always this, I don't know if you know the spherical cow joke, but the idea is that, I'm not going to tell this joke very well, but there's a whole conference talking about agriculture or something, and the agriculture specialist gets up and starts talking about cows. Okay, so the subject today is cows, and we're going to talk about what cows eat and stuff. And then the biologist comes up and says, well, let's talk about how a cow works, and there's two stomachs. And then the physicist comes up and says, let's model the cow as a point particle. And so that's the end of that joke. But the idea is that this thingy, car, is a big object. And there's even a person in there. Okay, so this is like the physical, the real life photo. And then what we do often in physics is we say, well, what's important? What are the things at the very most simple level that I care about with this race car? Well, I care if the racer is going to win, I guess, right? And so I care about its position, whether the car has crossed the finish line or not, and its velocity. And we can, I guess, simplify the entire car as being a point-like particle model. Point-like particle model. Because a particle has a position in space, an x, y, and z coordinate, and then it also has a velocity. So some velocity, usually a vector, that has a speed, a length of the vector, and also direction in which it's going. And you can get all of that, all the kind of really important stuff, by just saying, let's approximate the car as a particle. Now, it isn't a particle in real life. It's got wheels that are spinning, and there's angular momentum, and there's somebody turning the steering wheel, and there's friction and all these things. But to get started on a problem, you can make a model. So that's that. What else is in chapter 1? They talk a little bit about making rough estimates. This is section 1.4. And this can kind of come up. There's something about order of magnitude of the quantity. Is it's tens, hundreds, or thousands of the relevant units. So this happens a lot in physics. Sometimes it's called back of the napkin calculations. So you can imagine some physicists sitting, eating their lunch at maybe one of the great Chinese food restaurants on Spadina Avenue or something, and having a big discussion, and someone goes, oh, and they have a pocket protector and a pen, and so they take that out and start writing on a napkin. These are estimates. So you want to do one? I'm going to go on the Learning Catalytics now, and you can see that session ID, and I'm going to deliver this question, which is, I guess you could look it up, but just, I want you to estimate, look at these numbers, A, B, C, D, and E. They're wildly different from one another by factors of 10 or more. And think about water and what a kilogram is and what a meter is and what a cubic meter is. So that the M3 means a cubic meter. What's the density of water in kilograms per meter cubed? Give a minute to think about that one. Feel free to discuss with. So while we're at it as well, let me discuss a little bit about these learning catalytics questions. So first of all, if you can get in and answer these questions, I've set it up so it's 80% for having answered any question at all is like the points, and then an extra 20% if you also get it right. Here's my 1 minute. Second of all, there's an asynchronous option for anybody who's on the video up there, which are the exact same questions, but to be done at your leisure. And so at the end, you only have to do one or the other, but if you were to do both, you would just get the maximum of whatever one you did. So there's that option as well. And secondly, or thirdly, there's this limit of the number of these online points that you can get of 2/3 of the available ones, and then beyond that, you're capped out. So if you are really having some technical difficulty getting in right now, please don't get too stressed out about it. But I can see that some of you have answered. So let me just stop the delivery. So sorry, this question is going to stop in, I'll give you a 5-second countdown. 5, 4, 3, 2, 1. Only got 118 responses, so that's not very encouraging. But this is sort of what I'm seeing is of the 118 out of the 900 students in this course that were able to do this, 65% of you got E. So hopefully more people are able to find this as time goes on. Can you say that again? Yeah, that's another thing. It's fine. If you do the asynchronous, that also works. Okay. It just won't show up in my histogram. So maybe there's some people that are working on the asynchronous version. But you're supposed to be doing the Con Hall one. So and this is the idea, is that it seems like it would be a lot, right? A cubic meter of water, if you think you can hold a kilogram, a kilogram is 2.2 pounds. A cubic meter would be like a whole bathtub full of water, and it's going to be kind of a lot. I guess in my mind, I might have estimated 100, but it's actually 1,000. 100 wasn't a choice on that list, so it's 1,000. So density is something we will be talking about. It's amount of mass per unit volume of a material. And there are different units. So you may have memorized the density of water is 1, and that is correct if you're using grams per centimeters cubed. Grams per cc, that's correct, it's 1. But when you do the whole conversion up to meters cubed, there's more than 100 centimeters cubed in a meter cubed. There's actually like a million or something. There's a lot. Because you can think of all those little cubic centimeters that get lined up in all 3 dimensions, right? So, I think that's maybe where I'll leave you on that. Yeah. Oh, really? 2727. Oh. There may be 2 kind of going, right? Because there's the async, but I think that this is the one that's supposed to be the Con Hall one. Either one works, though. Okay. We're getting used to how this system's going to work. But at least 118 of you are going to show up in that histogram. And when the dust settles, we'll see how many got points today. Because I'll just combine the async with the Con Hall. And I'll give you the maximum if you do both. I will talk a little bit about significant digits. Now, the issue with this is that it's sort of, these are the rules, I guess, of this textbook and sometimes of the Mastering Physics homeworks and things. The real rules of experimental physics are more in that uncertainty document that Professor Roya sent off, but they're similar. a significant figure is the number of, I guess, reliably known digits in a number. And you can usually sort of figure this out by the way the number is written. So for example, it's best to do these with examples. 23.21 has 4 significant digits. You just count the digits. 1 and 2 and 3 and 4. So that's good. So I'll just put a check there. Where it gets a little confusing sometimes is if there's zeros. And so example, 0.062. It turns out that in that, it only has 2 significant digits because the first 2 zeros don't count. And the reason that they don't count is because they're just considered placeholders to give you sort of the order of magnitude. There's no way to write down 0.062 without putting that 0 there in the front 0. You didn't measure it, you just sort of know the thing. And so what you can do is you can, if you're confused, is convert to what's called scientific notation. Scientific notation is 0.062 equals 6.2 times 10 to the, wait a second here, 10 to the minus 2. So when you see it in scientific notation, then you can just count those digits out here and see that there's 2. So that's one way of counting significant digits. And then sometimes you see a 0 after a first number, but before the decimal place. For example, 80 kilometers. And I think that's unclear or maybe ambiguous or something. It could mean 2 different things. It either means that you measured 80 and that it's not 81, it's not 79, and you feel pretty confident that it's plus or minus maybe half a kilometer or something like that, in which case that would have 2 significant digits. Or you might have rounded, right, and said, it's around 80, and what you really mean is that it's kind of more than 75 but less than 85, and somewhere in that range, and you've rounded to the nearest 10. I don't know. So it's either 1 or 2. But if you did really know it, I guess you could put a 0 after and say, that has 3 significant. So this is 1 or 2, and this one has 3. And that one we don't quite know yet. But really, if you're making a measurement in practicals, you should just write a plus or minus to tell you what the uncertainty actually is, and then you will know how many digits are significant. And then there's these rules. So let's for propagating. Anyway, I'm still kind of going through chapter 1 here. It says, when multiplying or dividing numbers, the result has as many significant digits as the number used in the calculation with the fewest significant digits. Okay, so what does that mean? So, again, let's do an example. Let's say you're finding the area of something and of a rectangle, and you have measured 2 sides of it. You know it's a rectangle, so it should be length times width to give the area. And you measure 11.3 and 6.8, and you get 76.84. That's what comes up on your calculator. So what Akina is telling you to do is that you should round it. Not really sure exactly why you should round it, but it is a rule, is to round it. I gotta say that when I was a PhD student, I never rounded anything in my lab notebooks. I just leave all the significant digits because why not, right? Just write them down. I think probably in my heart, the best answer is 76.84. But what bugs some scientists about this is that it sort of implies that you really precisely know what the area of that rectangle is, down to the 100th of a centimeter squared. But you don't really, right? Because you only measured that 6.8 centimeters. And the 6.8 is probably a little shaky. It might have been 6.7 or something. So what Akina is saying is that you should probably round it to kind of be more honest about what you measured. Unfortunately, the downside of this is that it introduces rounding error, and that's why I never did it in my lab books. But anyway, you could say 77, and that's maybe better. Anyway, it's rounded to the correct number of significant digits. You follow what I'm saying there? It's a rule. And then there's two more rules. Well, there's one more rule, which is that when adding or subtracting, the answer is no more accurate than the least accurate number used, meaning that you go with the column or the hundreds column or the tens column of the least accurate thing. Anyway, number of significant digits could be off by 1. You could have rounded this to maybe 76.8. I'd be okay with that. Want to do another? See if another, again, I'm in the Con Hall version here. If I go to 2 and deliver this one, you might see question 2, which is this bunny racing versus the turtle. And this one is, it's using one of those equations from ESA, which is, what is it? Remember that equation I told you, V equals D over T? You're here using the equation, you're changing it to D equals V times T. So that's the equation. So what you're going to do is you know that V is 25.1 centimeters per second, and you know that T is 4.512 seconds. Somehow, I don't know who did this, but they measured the time to the thousandth of a second. I don't know how you could do that with a real bunny and a real turtle, but anyway. The question is, when you multiply those, the answer is 11.325. I can just tell you that. What should you actually type in, or just, I guess, to your mastering physics to get the right number of significant digits? I think you can type in anything, you still get the points, but it gives a little complaint on mastering physics that the answer you typed has the wrong number of significant digits. And so if you want to avoid that warning, which one do you type? Ooh, we're up to 166 in Con Hall. All right, it's a little silly. Let me just show you what I see on my screen here. So, right, so the basic idea being there that the least, I guess, accurate number was the 2.51 centimeters per second. It has 3 significant digits, and yet the time has 4 significant digits, so you should round to 3 significant digits. So you round the 11.325 down to the nearest, which is 11.3. I don't know if you guys can tell, but I don't like significant digits very much. I'm anxious to move on to physics. But let's continue a little longer. It sort of depends who you get for second year physics, if they care about this stuff or not. So the answer is C. 3 sig figs, something like that. I'll just leave it open. Again, scientific notation. So whenever you use scientific notation, then it's very easy to count. You don't get ambiguous results. So, for example, again, 36,900 is a bit ambiguous. If you write 3.69 times 10 to the 4, then it's very clear that number has 3 significant figures. Or if you were to write 3.690 times 10 to the 4, now the 0 is significant because it's kind of trailing, and you had a choice whether or not you were to write it. So if you wrote it, it must mean you measured it. Does that make sense? Anyway, it's there in the scientific notation, so you count it. And I'm going to do an example, which also has some unit conversion. So, and this comes from what I thought was a cute picture of my daughter. In the playground near my house is Baird Park, which is, there's this, I'm zooming in on the sign here, which is no smoking within 9 meters or 29.5 feet of playground. So maybe you really shouldn't smoke so close to the playground that you're measuring 0.5 of meters. But anyway, the point is there's something wrong there. Those two numbers have different numbers of significant figures. So which is it? Okay, this is getting, we're going to get a little obscure here, but what I want to do is now go to the Toronto bylaw. Where the heck does it even come from? You can look it up. It turns out that it says, while in a park, no person shall smoke within the boundaries of and a 9 meter radius. So it's 1. It's the real answer. So we can do it. Here's some, let's convert 9 meters to feet. So feet or foots are a unit of distance, which you may not know about, but you can figure it out. There's something called inches, and there's a definition, which is 1 inches equals 2.54 centimeters. So you can, whenever you want to convert from one unit to another, what I like to do is I like to set up a ratio that I know equals 1. And then I can multiply by that ratio and cancel out the units. So this is a good skill to have and to practice. There's also all these metric facts. And then there's also the fact that 12 inches equals 1 foot. And so 12 inches divided by 1 foot equals 1, or 1 foot divided by 12 inches equals 1. So what we have is that D equals 9 meters. So we're going to multiply that by 1 a bunch of times until we get to feet. Which is, so the first thing I need to do is multiply by something that has meters on the bottom. So I look around at my facts, and I see that I've got centimeters, which is 100 centimeters equals 1 meter. But I still haven't got to foots. So I can look around. I have meters. No, wait, wrong. Let's get this right. I've converted to centimeters. Now I want to convert to feet, but I still don't have it. So what I'm going to do is convert then to centimeters on the bottom, inches. We know for a fact that 1 inch equals 2.54 centimeters. Still not at foots, but then I can use the fact that I'll put inches on the bottom here, and feet here, that 12 inches equals 1 foot. And now, what happens, the way I've set that up, the meters cancels with meters, the centimeters cancels with centimeters, the inches cancels with inches, and I should get the answer in feet if I just multiply and divide all of those things. So, if you'll follow me along, it's 9 times 100 times 1, divided by all that stuff. 1 times 2.54 times 12. And if I type all that into my calculator, I get, well, I'm going to get 30. D equals 30 feet. And that's to the right number of significant digits. Or better, that's still ambiguous, right? You should really say D equals 3 times 10 to the 1 feet. And then it's clear there's one significant figure in that. But no one's going to write that. But that's better than saying 29.5, I think. Is there anything left? Yeah, there's one more thing, which is the problem-solving strategy, which is at the end of chapter 1. Then we're done chapter 1. Okay, problem-solving strategy. Now this is a suggestion, which is really, really helpful, I think, for solving problems in this course, is trying to set things up in a way that works for lots of different problems. So what will happen to you and what happened to me is that you'll open up your term test someday and see a problem for which you do not know the answer. And rather than what happened to me, which is I just started feeling super, super nervous and sweating and freaking out completely and going into panic mode, which activates the deepest part of your brain that just wants to fight or flee, what you can do is calmly try to do some things. These 4 things. Draw a diagram being step 1. And I find that when I'm doing things, I get less nervous. Like, for example, when I come into this class and I have to walk up on the stage and wait to talk, I feel kind of nervous because I'm going to be doing public speaking. But right now, I feel pretty calm. Here you are, and I'm just talking. And so when you're doing stuff, you forget about being nervous. So, draw a diagram. Okay. Write down your knowns and unknowns. This is giving you stuff to do, and it's important work, which is going to help you find the answer. The next step is, well, you're going to neglect some irrelevant details and choose some sort of representation. You're going to model things, model the turtle as a point particle or something, okay? And then the third step, this is where it takes practice to do this step, is to write down the relevant equations, things that are going to help you really get the answer. So maybe you have that aid sheet that you wrote out a lot of equations on. You're going to find sort of what chapter we're on. I know this is a chapter 3 question, so maybe we could use this equation right here. And it seems to have a lot of the same letters in it as my knowns and unknowns that I had up there. Okay, so we're making all this progress. And if you're showing all your work, all of this work you're showing is worth points to the, that marker who's going to be actually marking what you wrote on the term test. So that's good. And then it's kind of like solve. So find the answer, plug in the numbers. Also, sometimes a final step is to sort of do like that sanity check. Really, should a whole cubic meter of water weigh 1 kilogram? Does that make sense? Not really, right? And so that's called a sanity check. You sort of think, does it sort of make sense? Or you find the height of the CN Tower is 10 to the 50 kilometers or something. It doesn't really seem to, maybe there's something missing in one of my equations, and you kind of go back. And so what you will see if you keep going in this textbook is that every single example she puts has this same structure of how they go through it, this problem-solving strategy. So, example 5.6, first step, sketch and translate. And then second step, simplify and diagram. Third step, represent mathematically. Fourth step, solve and evaluate. And it's through the entire textbook. So through Physics 131, all through the end of Physics 132 up to special relativity, they're applying these same kinds of steps sort of in different ways. Sometimes, you're doing slightly different things. But this is a way of systematically setting things up and calming yourself down so that you can do this stuff. Anybody can do this. Anybody can draw a little diagram, right? It doesn't have to be beautiful. My diagrams are like circle or line because I'm not that good at art. So, and that's it for chapter 1, I think. What time is it? Oh dear. Okay, we're running a little behind. Okay. So chapter 2 is about describing motion. So motion is a change in an object's position over a certain amount of time, or during a certain change in time. And there's always an observer. Physicists often say that motion is relative. So there's that joke, why did the chicken cross the road? Or wait, did the chicken really cross the road, or did the road just pass underneath the chicken? Because from the chicken's point of view, the chicken is at the center of the universe, right? And the road just goes by. So who is the observer? That's actually from Einstein's theory of relativity. All motion is relative. So I want to talk about making a motion diagram, and I have a quick little demo I'm going to try to do on the video. An easy way to study motion is to make a video of a moving object. And so this is an old-style film reel where we can see different instants of time. And most videos are like something like 30 photos per second, and you just watch them one after another, and you see this motion. So, for example, the car is at a different position at each different time because it is moving, whereas the tree is in the same position at each time because it's not moving. And what you can do is kind of stack them up on top of each other, and this is what's called a motion diagram. Or, even better, replace the car with dots for the point-like model, and you get a motion diagram like that. You want to try to do it on the with the beanbags? This is where the penguin comes in. I don't know how my videographer is doing with tracking me all over the place. Tick, tick, tick. So the idea here is that I'm going to move around this cart and try to keep track of its motion with the motion diagram by dropping beanbags. Look at all that friction. That's not good. So if I go kind of fast, let's see. I kind of have to get in the groove here. And then throw beanbags. This is not easy as it looks, but tick, 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 tick. Okay, so these beanbags, I don't know if you can kind of see them, are a motion diagram representation of where that cart was when I heard the ticks. Now, if I was to do it slower, what would happen to the beanbags? Take the same cart, and I'll do it kind of slowly. Tick, 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 tick. Whoop. I don't know if you can kind of see. They're a bit closer together because the cart didn't move as much during those same ticks. So that's a motion diagram. And I have a couple of little, thank you. Can we go back to laptop one? So glad you're here. Okay, I need my little pen thing, which of course I've lost by now. Where did I put it? Oh, it's right here. Got it? I need one of those strings like for your mitts. That's cool. So that you can. So this is looking at these two motion diagrams. Whoops, can't deliver. Which object has the higher speed? You can feel free to check with your neighbor during these. These are once you've thought about it. What time is it? Just give you another 30 seconds to click into this one. And then I've got another one, a little harder. So just this last 5 seconds. 4, 3, 2, 1. And stop. So a lot of people are answering. Whoop, sorry, this one. Oh, wait. I think I completely screwed that one up for the Con Hall one. Anyway, the answer is B, because it travels a farther distance between the same intervals of time. So I think that what I did on learning catalytics is essentially the wrong question, which is the next one. Yeah. Okay, I'm getting used to all my laptops up here, and it kind of messed this one up. But the idea is when the beanbags are farther apart, the thing's going faster. When there's acceleration or deceleration involved, this is sort of what I tried to do. Deliver again. Is which object is speeding up? And we can sort of try this by maybe propping this up a little bit. So if I try my penguin again, here I am throwing people off. If I were to release this from rest, Okay. I guess the beanbags get more further spread out as we go towards the left. Can't really see it too well there. But you see getting further spread out. The other thing I could do is I could launch it from the left side and give it an initial velocity towards the right. Okay. And I got the exact same beanbags. Does that make sense? It's sort of weird. It's going, we don't know, I guess this would be the first beanbag, second beanbag, third beanbag, and we kind of know that. But if all you see is the dots, this could have been the first, second, and third for going that way. So the answer I was going for was E there. So okay. And then we're just going to leave that at that and send this to all. Okay. So we don't know which direction the object is traveling. If we had some additional information, like little numbers on this, 1, 2, 3, 4, then we would know this one's slowing down. And if this said 1, 2, 3, 4, we would know that this one is speeding up. So if the numbers on or if the points on your motion diagram are numbered, which they probably should be to be a good motion diagram, then the answer then would have been that B, right? So with numbers, the answer is clearly B. But the correct answer I was looking for is C, because I didn't number it. Okay. So the next thing that I would like to do is go on to making graphs of this stuff. Oh, here we are. This is with the velocity vectors. So here is something which we know is traveling from left to right, and you can see now that there's a velocity vector. So that includes not only what the speed is, we know this one's going faster than the hare is going faster than the tortoise, but it also includes the direction. We know that both of these objects are going towards the right. So rather than just numbering 1, 2, 3 with the motion diagram, you can also just specify the direction by putting in these velocity vectors, and we'll talk a lot more about that in chapter 3. And what I want to talk about on Wednesday, and I'll start off with this on Wednesday, is making position versus time graphs. And so if you move something, you can get a position versus time graph. And I think that is all I will sort of say about that. We'll just send this for a second. What I want you to do between now and Wednesday, is read a bit about vector math. We're going to continue on in chapter 2. Position, displacement, distance, and path length. This is one of the things, if you took high school physics, you might find a little different about this textbook, is there's a difference between distance in this book and the distance that is often defined in high school physics. And something to think about is, does constant velocity imply constant acceleration? And does constant acceleration imply constant velocity? Sort of think a little bit about what's the difference between velocity and acceleration. If one's constant, doesn't mean the other's constant. And I'll see you on Wednesday at 11.